So we're going to start our last problem relative to Chapter 17 in Newton's Law. So what I have here is, here I have a sort of a spool, kind of a complex spool. So we have two radii on the spool, a small one and a larger one. And so on the smaller side, which is smaller radius, which exists on both sides, we have wrapped up, and the cord is being released. It's connected at the ceiling, so this is just unwinding here. And then on the larger radius spool, we have a separate cord that's connected to a box that's hanging here, a crate. And so as this thing unwinds, the bigger one will also unwind and be dropping B faster than the original spool is falling. Now I said we have two radii. The smaller one radius is 1/2 meter, and the larger one is 1 meter. All right. For this problem, we're told that the mass of this complex spool is 30 kilograms. The mass of this crate box is 5 kilograms. The mass moment of inertia about the center axis of the spool, 20 kilogram meters squared. Here we list the two radii, and we're told ignore torque relative to the supports. So here's the point, is that if we look here, there's definitely lots of mass there. That would tend to make everything shift over, and so we're basically being told to assume that all the ropes are coming down vertically. Okay? So we'll stay with that assumption. And so the first thing we then need to do is free body diagrams. So those are fairly straightforward. So if we look at this from the side, right here, there's two ropes holding this up on both sides, so I'll call the ropes on the sides T1. So I have two T1s, two tensions, and I'll let that connect at this point P here. Out of the center of the spool, we have our 30 times G for the weight of the spool. And then we have this, the rope coming off, we'll cut the rope and put a tension in there. So that's tension 2, which is related to the box B. Looking at box B, we have it is 5 kilograms, so 5G is the weight, T2 is the tension that's supporting it. And so we're ready to start writing equations. That's all there is. All right, so applying Newton's rule conventionally, there are no forces in the x, so we can ignore that. So looking in the y, we have 2T1 minus T2 minus the weight of A equals 30 times the acceleration of A in the y. Now if we look at this equation, this introduced 1, 2, 3 unknowns. So now we'll take the moments here at the center, because this thing is rotating, and relate that to I alpha. So if we look relative to the center, these two tensions would take it clockwise. We have minus 2T1 times 0.5. That would be from the center out to where the cord is. T2 is 1 meter out, and that would take us clockwise as well. So minus 2T2 times, or said that wrong, minus T2, tension 2, times 1 meter. And we're left then with mass moment of inertia is 20 times alpha A, which we don't know. So we've just added one more unknown here. So we didn't gain any traction in that. If we go to look at B, we can sum forces in the y. That's all there is. So we have T2 up minus 5G equals 5 times the acceleration of B in the y. So another equation, we added another unknown. We didn't gain any headway. So we need two more equations, and we'll have to appeal to kinematics to make that happen. All right, so how are we going to do that? Well, notice what we have here is, let's just go up to this point. This cord is not moving. As cord comes off of this, we realize this is an instant center. All right, and so at this point and everywhere above it, acceleration is 0, velocity is 0. All right, so this is the instant center for what's going on. All right, so when you look at it, let's look at it from the side, it's really like this whole rolling mechanism is rolling along a wheel coming down along this cord. Okay, it's like we have a vertical road and it's just rolling down. So this point here, as it gets there, as the cord comes off, keep in mind, if you're rolling without slipping, which this will definitely be doing, the acceleration in the y here, okay, will be 0. Okay, if you were on the roller, you would have omega squared coming back, but tangentially, the moment you come off that roller, your acceleration stops. Okay, we're assuming it stays vertical, so on this cord, there's nothing in the x, there's obviously nothing in the y. All right, so that's one of the first big observations that we can make. And so if we do that, this takes us to the following. So what is the velocity here in the center? Well, the velocity here is 0, so velocity here would be omega times the radius, 1/2. Now we don't need velocity, but if we take the derivative, we get the following. The acceleration of the center of mass here in the y is simply alpha times 1/2. So we go from here, and we get alpha times 1/2. All right, alpha cross r, that's what it gives us. Now, if alpha was counterclockwise, that would be positive. Now, we expect we're going to find that alpha is going to be clockwise, so that'll produce a negative, which would give us acceleration of g on roller A going down. It all makes sense. The signs will work for us. Whoops. Let's bring that up. Okay. Once again, as we said, if you're right here, this is an instant center. Also, the acceleration is 0. All right, so to get the velocity here, based on instant centers, as it were, you get VA is omega times r. Take the derivative, AG equals alpha cross r. Okay. So, that's good. So we added one equation. I need one more. And so one of the standard things we need to do when we have two masses is to relate the acceleration, I'll just go in here, of what's happening here to the acceleration of what's happening down there. So that's what we're going to do. So we know the acceleration here was 0. We now know the acceleration of y is basically alpha cross r, alpha times r, but we know the acceleration here. So let's look at that. If I were to go from here to this point here, whatever the acceleration is over here, the acceleration here is exactly the same. So that'll allow us to relate the acceleration of A to B. That'll be the last equation we need. And we do that in the usual way. The acceleration at B in the y, right here, is the acceleration at G plus alpha cross r. All right, now let's understand that. As the rope comes off of here, if we stayed on the roller, you would have anything in the roller has an omega squared r going back. But as a rope comes off of here, it loses the omega squared r acceleration. So from here to this edge of the rope coming off, it's just there plus an alpha cross r. And that's what we have here. So we had AG was 1/2 alpha A, and then we go out 1 meter, and so that will give us, if we did the alpha cross r, we get 1 times alpha A, so it's in all 3/2 alpha A is ABG. Okay? And then we'll note further, we can get rid of the alpha A term, or we could keep it, just depends on how you want to go about it. But we can obviously go up here and substitute AGY for this. And so that would give us alpha AB in the y is 3 times AG in the y. We can use that if we want. We now have enough equations. Everything is simply a matter of solving all the equations and unknowns, which is no doubt lots of fun. But we'll just appeal to the bottom line. And if you go through all the math, you will find the following. AG, this is a little hard, very hard to read, is minus 2.845 meters per second squared. And AB is minus 8.544 meters per second squared. The contrast that the camera is picking up is very poor, but when you see this on the paper, if you print out the PDFs of the lecture notes, you'll see it very clearly. That takes us through Newton's law. So where are we now? We've done basically 3 major topics. The first midterm covered 3 topics. The second midterm covers 3 topics. What are they? Namely, relative velocity and acceleration analysis, or relative motion analysis, Coriolis acceleration, and then Newton's law. So your second midterm, we are now ready to contemplate that. You need to have a little time to work the problems for Newton's law, but go on the internet, you'll find when this is scheduled. But you are going to be getting an exam with 3 problems. Now what I will note here is that if, to the extent you have things like you had in this problem here, you have kind of like pulleys, so you could be having absolute motion analysis as you have with pulleys. You may find, as in this problem, that instant centers and kinematics are needed to give you more equations. But 3 core problems, but everything from the past is still fair game as we look to put the tools together to solve these problems. So we'll be talking again shortly, and we'll start our next chapter, which is energy, here very soon. Talk to you later.